Hi, my name is Kristen. Welcome to this journey through digital product design and to 3D printing. Today, we are going to study the chapter, which is Introduction to Modern Product Design. In this chapter, we'll explore the essential concepts that shape how products are digitally designed, prototyped, and manufactured today. From CAD tools to teardown analysis, we'll understand how engineers bring ideas to life in the modern world. Let's begin. 2. What is digital product design? Digital product design is the complete process of creating a product using computer-based tools. This includes creating digital models, testing them virtually, and preparing them for manufacturing. It's faster, more accurate, and collaborative. In mechanical engineering, this approach has become the industry standard. 3. CAD, computer-aided design. CAD is used to create detailed 2D or 3D models of a part or assembly. Mechanical engineers use software like SolidWorks or Fusion 360 to visualize and refine the geometry. CAD acts as the base for analysis and manufacturing. It helps identify design flaws before physical prototypes are made. 4. CAE, computer-aided engineering. CAE involves simulating how your design behaves under stress, heat, or vibration. Using tools like ANSYS or ABEX, you can test and optimize the product before real-world testing. It saves time and cost by avoiding failed prototypes. CAE ensures your product will perform reliably. 5. CAM, computer-aided manufacturing. CAM converts your CAD models into machine instructions. These instructions guide CNC machines, or 3D printers, to manufacture the part. CAM allows for accurate, automated, and repeatable production. It closes the loop between design and reality. 6. Comparing CAD, CAE, and CAM. Think of CAD as the digital drawing board, CAE as the testing lab, and CAM as the factory floor. All three work in sequence to bring ideas into physical products. Mastering all three helps mechanical engineers become full-cycle product designers. 7. What is design thinking? Design thinking is a creative process to solve user-centered problems. It starts with empathizing with the user, defining the problem, brainstorming ideas, prototyping, and testing. It emphasizes experimentation and feedback. Engineers must think beyond functionality and consider the user experience. 8. The 5 phases of design thinking. The 5 stages: empathize, define, ideate, prototype, test, are not always linear. For example, after testing, you may return to ideation. This flexible model encourages innovation and human-centric solutions. 9. Product Life Cycle Overview. The product life cycle consists of development, introduction, growth, maturity, and decline. As an engineer, you must consider how your product evolves over time. Will it require updates? Will it become obsolete? Planning for the full life cycle is crucial. 10. Life cycle and engineering decisions. Design decisions made early affect everything later, from production cost to recyclability. For instance, choosing a complex material may increase both performance and cost. Understanding the product's journey helps in making informed trade-offs. 11. Rapid prototyping. Introduction. Rapid prototyping is the process of quickly building physical models from CAD files. 3D printing is the most common method used. It allows engineers to validate form and fit before moving to production. 12. Benefits of rapid prototyping. It reduces the risk of design failure and speeds up product development. Iterations become easy. You can tweak and reprint within hours. It's a low-cost method to test new ideas and present concepts to stakeholders. 13. Industrial design versus consumer design. Industrial design focuses on function, robustness, and efficiency. Consumer design emphasizes aesthetics, ergonomics, and emotional appeal. For example, a drill machine and a smartphone differ in user priorities, even if both use similar mechanical principles. 14. Engineering roles in both domains. As a mechanical engineer, you may work in both domains. For industrial tools, precision and longevity are critical. For consumer products, look and feel also matter. The design approach changes depending on the user and context. 15. Design for manufacturing, DFM. Basics. DFM ensures that products are designed in a way that's easy and economical to manufacture. It considers factors like material selection, tolerance limits, and assembly complexity. Simpler designs often lead to better manufacturability. 16. DFM techniques. Using standard parts, minimizing tight tolerances, and designing for ease of assembly are key practices. DFM bridges the gap between engineering intent and shop floor reality. It's essential for scaling up production. 17. What is reverse engineering? Reverse engineering involves taking apart an existing product to understand how it works. It's often used when documentation is missing or when you want to learn from a competitor's product. Engineers scan or measure the part and recreate its CAD model. 18. Applications of reverse engineering. It helps in redesign, quality improvement, and even legacy part reproduction. In automotive or aerospace sectors, it's common to reverse engineer old parts to build replacements. It's also useful in benchmarking and patent analysis. 19. Product teardown. What and why? A product teardown is a physical disassembly and analysis of a product. Engineers perform teardowns to learn about component choices, material usage, and cost-cutting methods. It's a hands-on learning tool. 20. Wrapping up. What you've learned today. We covered how digital product design works, from CAD to CAM, and from empathy to engineering. You now understand how a product is imagined, simulated, tested, prototyped, and manufactured. Whether designing consumer gadgets or industrial tools, these concepts give you a modern edge. In the next chapter, we'll go deeper into 3D printing processes and material selection.